Right. So moving on to the physical chemistry question. So nowadays you will keep having these questions in part 3. So there is a equation that is given, A, B, and C reacting to form D and E. So the stoichiometry is given. So they are trying to measure the kinetics of these reactions, how fast this reaction using initial rates. So that is the normal method. So they have carried out 4 experiments here, and the initial concentrations are given. And they also have found delta A naught, which is the concentration difference after this period of time for the reactant A. And what they are asking here is calculate the initial rates. So the rate can be expressed in terms of either reactants or either products. For an example, in terms of A, we can express as dA, the concentration change of A with respect to the time taken. Okay, will be equal to rate of this reaction. Similarly, so when this is consuming, so you can even put a negative charge in your expression. But when you have the difference that is given as 0.04, automatically this entire part will become as 0.04, which they have given. So please put the units when you are plugging into equation to find R1 to this particular experiment. So you can divide it by 50 and you will have R1 as 0.04 over 50 means it will be like okay, so 4 over 5,000. Okay, so this will be around 8. 40 over 5 is 8, so 8 into 10 to the power minus 4, right? MOLD minus 3 per second. So you need to write these values here, R1, R2, and R3, and R4. So the point here is when you have this type of a reaction, you can write rate in terms of A, or either you can write in terms of B, either C, either D, or either E. These rates will be negative, these rates will be positive in your expression. So what they have done here is they have measured the concentration change of A within these time periods. Okay, so that is what they have given here. So the concentration change for the experiment 1 with respect to A, and you divide it by the time to get the rate with respect to A. But this is an overall reaction. Okay, so in the overall reaction, you can write the rate with respect to A, B, C, D, or E. Anyway, when you write the rate with respect to each component, at the end of the day, the rate of the overall reaction should be same. Okay, if you write down the rate as this, and you can write down a rate with respect to let's say B is delta B concentration over dt. Okay, so when you find the rate with respect to B, and then when you find the rate respect to A, since this is the same reaction that is happening, this rate and this rate should be equal. Okay, you should know that. That is how we normally write. But if you want to equalize the rate of this one and this one, what you have to do? You have to divide this by 1 over 5, because the stoichiometry here is 5. So we get the reciprocal in order to equalize rate with respect to B and rate with respect to A. Okay. Now here this is not equalizing. You just write down the rate with respect to A and rate with respect to B. So you don't need to put this 5 here. Okay. You just need to put delta B. So the idea of this entire question is you need to understand you can write the rate with respect to A or either delta A. That is very straightforward, right? So you can find the rate of these R2, R3, and R4, right? 0.096 over 60, 0.128 over 40, 0.08 over 25. So you will have all the rates. and then taking A, B, C as orders with respect to each component. Now we are going towards the rate law. Okay, so you can write down rate law as R into R is equal to K into concentration of A to the power A, because they have given the orders, then concentration to the power simple B, the concentration of C to the power simple C. So this will be our rate order. And what you have to do is you have to calculate A, B, and C. Okay, so what you can do is you write down the rate law for these four experiments. So the first one will be 8 into 10 to the power of minus 4 is equal to K times, what is the concentration of A? 0.2 to the power A, 0.2 to the power B, 0.2 to the power C. So that is experiment 1. This is normal way that you know. Then you write down for experiment 2, 3, 4, and you divide 1 by 2, 2 by 3, or however 3 by 4. You find the order with respect to A, B, and C. Okay. For an example, if you take experiment 1 and experiment 2, so here you see the concentration of A is changed, B and C kept constant. So automatically from experiment 1 and 2, you will find the order simple A. Okay, and then when you consider about experiment 2 and 3, you see when you consider about experiment 2 and 3, A and C kept constant. So from this you find B. Okay, and then when you want to find C, so you can take experiments, what you can take. C, the only change is here, 0.2 to 0.4. So you have to take experiment 3 and 4. However, at this point, you know A and B, right? So automatically from equations 3 and 4, you can find simple C, because you know A and B in the equation. Okay, so when you divide it, the only thing that you don't know is C, right? Did you get my point? You have the rate, so you know these two for two reactions. You don't know K, but you know concentration of AB for these two reactions, and even you know A and B for those two reactions, and even you know the concentration of C for those two reactions, those two experiments. The only thing that you don't know is C. Okay, so what you have to do here is you have to write down the equation and check whether you can get the result. So when you do this, A will be equal to 1 and B will be equal to 1 and C will be equal to 2. Okay, when you do the calculation. So this is normal theory. Okay, when you should learn this in your theory class. Okay, and state the overall order. So you know overall order mean A plus B plus C. So typically the overall order is 4. One thing I have to mention here, you will never see practically this type of reaction where the overall order is 4. Okay, because it is very, very rare. Normally we go for like 3, 4, very, very, very low. And then calculate the rate constant. So all these becomes theory. So you can select one of these reactions. For an example, if I select R1, so you know R1 is 8 into 10 to the power minus 4. Okay, and this will be equal to the rate constant now, and concentration is 0.2 m. You need to put all units here. Okay, and then to the power 1, then 0.2 to the power 1, and 0.2 to the power 2. So the only thing that you don't know here is K. So you can find rate constant using that. Okay, so the important part is part B. Okay, so because this part B is normally not in your syllabus, this is actually little far away from that. This is normally at university level. So in another experiment, if the concentration of A not is used as 10 to the power minus 3, B is used as 1m, C is used as 2m. Show that the rate expression of the reaction can be given as rate is equal to k dash a to the power simple a. Okay, so I will anyway use the board here for the explanation. The idea is this. Now, I will check the equation. So this one is, so you have the reactant A, which is going to react with 5B and plus 6CAQ, and there will be the products. Okay, so normally what we do here, we write down the rate law. So our rate law is R is equal to simple K time concentration of A to the power simple A, B simple B, and C simple C. Okay, so this is the normal way. Now in this one, what they have done here is when you use the concentration of A as 10 to the power minus 3m and B as 1m, C as in fact it was 2m, I guess. Where is it? Yeah, C is 2m, right? Show that you can write this rate as k dash time a to the power a. Okay, so this is critical. Why? Think about the fact. Now I'm going to put values here. Let's say this entire reaction happens in 1 decimeter solution. Okay, so how many moles of A is present? That is 10 to the power minus 3 moles. I'll put moles because this is 1. How many moles of B is present? 1 mole of B. C, 2 mole of C. Okay, now think about the fact when this reaction happens completely, you can imagine there will be no A remaining here because A is 10 to the power minus 3 and it will be consumed. No A. But B, it will be 1 mole minus 10 to the power minus 3. And C, it will be 2 moles 10 to the power minus 3. Okay. So based on this, you can imagine when A is consuming at a rate, the consumption of B and C can be negligible because 1 mole minus 0.001 mole is 0.999 moles. So this is negligible even if all A is consumed. And in case for C, it is also very same. Okay, so it is like when you have 100 moles of this and 100 molecules of this and 100 molecules of this, and here there is only 2 molecules for an example. Okay, so from these 2 molecules, 1 molecule is reacting, so only 1 molecule is remaining. So there is a big change because there is initially 2 molecules and now when it reacts there is only 1 molecule. But here you have 100 molecules and here you have 200 molecules. Only one is going to consume here, only one is going to consume here. So at the end there will be 99 here and here there will be 199. So this is very similar to the earlier case like 199, 200, 199. So there is a negligible difference in the concentration. Okay. So what you can do at that case is you can assume concentration of B as well as concentration of C is to be a constant. Why this is constant? There is excess amount of B and C. When A reacts, the concentration change is negligible. Okay. So if this is constant, the rate constant is another constant. So you can put this as K dash, which is expected that they have given. So your entire equation now becomes R is equal to this K dash new rate constant times A to the power A. Okay. And typically this rate constant we say as pseudo rate constant. Okay, so you don't have to know the name. This is called pseudo. Pseudo means partially correct, partially not correct, like partially true, partially not true. So partially true because all these concentrations are same. Therefore, this rate constant time this constant becomes pseudo rate constant. Okay. So did you get this idea? That is important to know. Did you understand this? I want your replies. Use the chat box very quickly. Yeah? Did you get this? Okay, so that is very important to understand. When there is excess amount of reactants than one of the other, you can consider their concentration as constant. So these become constant and this is another constant and it becomes a pseudo rate constant. So this is one of the methods that we use in our university to find the orders. Why? Because this can be used to find the order. Why? You keep the concentration of B and C excess, so it becomes a constant. So the only factor that is going to change here is concentration of A, because you should know this is a constant and you can find rate. So you know rate. When you change the concentration of A, you take delta A and you find the time and you take rate as in the question. And you know K1 dash because it is a constant. And the only thing that you don't know here is simple A. So you can carry out two experiments by changing concentration of A, and you can find the order with respect to A. That is simple A. Okay. So that is excess B and C. So how do you find B then? If you want to find B, you can keep C and A excess. For an example, concentration of C 2m, concentration of A 1m, and concentration of B 10 to the power 3 at one case or 10 to the power minus 4 in another case. Two experiment, then you can find B, because at that time your K dash will be concentration of C to the power C and concentration of A to the power A. So you can do this varying several times, 3 times in fact, you can find A, B and C. Okay, so this is one of the method that we use in university as a practical method to find the order. Okay, you can either keep the concentration of BC excess, AB excess, or AC excess to find ABC. That is a normal method. Okay. Right, so that is one of the parts that I wanted to explain in the board. So you can now write down. So you can write down the rate expression as the first one. Then you can tell K times concentration of B to the power simple B, concentration of C to the power simple B is a constant. And then you write down this expression. Okay, so K dash is typically the called silicon. State the assumption that made in deriving the expression 1. So here you have to explain the reason. Okay, so what is the assumption? Since the concentration of B and C is very high, okay, since B naught and C naught concentration are very high than A naught concentration, you can write the consumption of B and C is negligible. Okay, this one. And the second one, in the above experiment V1, the concentration of A changes with time according to the following equation. So here in this question, they have not told you how this concentration change, because we found that the order with respect to A is 1. So it should be normal first order change, okay, which the rate decays as this, and when you draw the equation graph, this should be this. So now they are telling the concentration of A changes according to the following equation, that is 2.2 2.303 log A. So this is concentration after time t. And there is a constant minus k dash t plus 2.303 log A naught. Okay. So this is the initial concentration. This is concentration after certain period of time. So they have given A naught is the initial concentration of A. Show that the half-life of the reaction is given by 0.693 and calculate this half-life by using the data given in A4 and B1 above. So B1 above means this reaction, this equation. Use that equation and using the data A4. What is A4? Using the rate constant here. Okay. So did you get an answer for this? Did you got an answer for this? What do you tell? Okay, so I see one no answer. Okay, so I will explain the idea. Okay, so I will stop the screen and I will explain. The idea is this, right? So what you have to understand here based on the information, previous information, I will tell you what is this equation and everything. So they have given this information 2.303 log A is equal to minus kt k dash t plus log A. Okay, I think it's 2.3 something log. Yes, 2.303 log A naught. Okay, and they are now telling to find the half-life. So first thing that you need to understand, what is half-life? T half, right? So T half means when you have your concentration, initial concentration C naught, drop to C naught by 2, the time taken. Okay, so how much time it is necessary to drop your concentrations from C naught to C naught by 2. Okay, so this is the equation that you need to use to find T half. Okay, now think about this. This is initial concentration and this is concentration after some time. So you can put here 2.303 log. You can put this here, concentration of A after T half. So what is this in terms of A naught is A naught by 2. And this will be equal to minus k dash t plus 2.303 log A naught, which is the initial concentration. And here for T, you can put here T half. Why it is T half? Because you are considering the concentration change from C naught, which is here A naught, to A by 2, which is after time T half. Okay, and then your K dash T half is equal to, I will get this here and I will put this here, and it will be 2.303 log A naught minus 2.303 log A naught by 2. So now this will become 2.303 log A naught by 2. So this becomes log 2. Log 2 is 0.3, and when you multiply 0.3 by 2.3, it will be 0.693. And your k dash t half becomes 0.693, and your t half becomes 0.693 over k dash. This is what they are expecting from you. Did you understand this process? First, tell me that. The first point that you need to understand is identify what is half-life. So half-life is concentration becoming half. So according to this information, this is initial concentration, this is concentration after certain period of time. So here we think this time could be half-life, which means half of A becomes A by 2. So that is what I have put here. Okay. And when I solve this, you will get this one. That's the idea. The only thing that you need to know is what is half-life and how you are going to put this into your equation. Okay. So did you get this? Okay, I have one answer saying yes. What about others? And here you should know how to solve log. So 2.303 I can take out. So log A naught minus A naught by 2 means minus. When there is a log minus, it will be dividing. So when you divide this, it will be log 2. So you can check log 2 in your logarithm book, and then you will see it will be around 0.3. And you multiply this by 2.3, you will get an answer 0.693. Okay. So remember, this half-life 0.693 over k dash, this half-life is for, remember, first order reaction. Okay, so if you remember your theory, normally first order reaction, the half-life is 0.693 over k, the rate constant. Okay, and we say for a first order rate constant, you can see the half-life is not dependent on the concentration of A, because there is no concentration term here. Can you see? There is no concentration term here. So either you use higher concentration or lower concentration. You need to understand T half is always constant. Why? There is no term here. Right? There is no term, no concentration term. Right, so this is one point I have to mention here. Okay, so these are very little bit higher level, but here you just need to know how to plug here and do the calculation. That's all. But I want to know, I want you to write something more here. Okay, so just look what I am doing, right? So when you have a reaction that is forming A to B, normally, let's say this is an elementary reaction. So here we write the rate law as K times A, right? At the same time, you can write the concentration difference of A over time as rate. So these two are typically equal. So since A is consuming, there will be a negative charge here. So normally I can equalize these two. Equal minus dA over dt. And what I'm going to do here is I will do this thing. dA over A concentration. Then I will integrate this to get KT equals, there should be an equal sign here, and this will be ln A. Okay, and the limit is from t is equal to 0 and t is equal to t. And when you do this integration, there will be ln A equals minus kt plus ln A naught So ln is equal to 2.303 log A is equal to minus kt plus 2.303 log ln A naught. So this is the equation that they have given to you. Okay, so these are not necessarily needed for you. What I want to emphasize is when you have a first order reaction that is happening, then you can write down using the rate law and write down using the differential form, and you can equalize and you can integrate and you can finally come to this equation. Okay, this is the equation that they have given to you. Okay, so what I want to tell you is don't worry about these methods. The only thing that they have given you is this. I want you to tell this information how this equation comes here. This equation comes here from this process. Okay, so that is one of the information I want you to give. I want you to give actually, because this is not A level, this is university level. So you study all these things in university chemistry. Okay, so this is rate expression for first order. Okay, so you in the same way you can develop this for a second order equation. There will be another equation that you can take when you draw this for a second order. Okay, and even zero order, and there will be two other equation that will come. Okay, I'm not going to tell about those two, but normally when I teach theory, I will provide these three equation, and to remember the students to understand the dependency of concentration dependency. Because if for the first order, when you put A naught over 2 here, then you find T half, there will be no dependence. But when you write down here as 2, then it will be like Ka2, and you change this A2, then there will be this change in again minus Kt, and 1 over A squared integration is minus 1 over A, and when you draw this reaction, it will be 1 over A plus 1 over A. Then you can put A naught over 2 here and find K T half, and you will see T half will be 1 over K A naught. And there is a concentration dependency for a second order reaction. So these things I'm not going to tell much. The only thing is you need to understand you can derive this equation which are given in your question. Okay, don't think it appeared from sky. You can derive this equation. That is why they have given directly the equation. You just need to plug the values and find T half. That's all. Okay, but I want to tell some additional information. This is how it comes. You don't worry about, you don't need to worry. So that's all. Okay. Right, so we will move on. Right, so this is very straightforward. Then you just need to put the values and find, because now you know you have found this one using this equation, and you need to put this rate constant here and find T half. That's all, because they have tell use the rate constant as this one. Even though it is just K, you this as K dash. Then you will have a rate T half value also. Okay. So first thing you take this one, then find T half.